Landscapes are rooted in their geology, the different rocks that form them, and the stories of these rocks are held in geological maps. These beautiful documents show, through their colours and symbols, the distribution of rocks, their different types and ages, as found at the Earth's surface. But they also tell us stories of tectonics, of major faults like this one, the Highland Boundary Fault, on the northwest edge of Scotland's central belt. Or here, on the far side of the Highlands, the Moyne Thrust and its structures that tell of periods of tectonic mountain building back in Earth history.
My name's Rob Butler. I work in Aberdeen, but I live on the edge of the Cairngorms National Park in northeast Scotland. The map over my shoulder there is part of the national park, and that big red blob in the middle is the granite massif of Loch na Gar. It's a landscape grounded in granite and sculpted by the act of glaciation into these fantastic landscapes of high corries, deep cut valleys and high plateau. I'd like to take you on a journey through geological mapping. We're going to end up in the northwest Highlands of Scotland. But our story is going to be fairly wide ranging.
These maps tell wonderful stories of scientific discovery and argument. But before going to look at these areas in the northwest, maybe we should ask the question, why do geologists make maps at all? Or more critically, why does society commission geologists to do that? Well, here's part of the world's first countrywide geological map, the very famous one by William Smith and published in the very start of the 19th century. It tells us where the different rock units are, which is a mixture of stratigraphic age and rock type. So it tells us about different earth resources and the challenges facing engineers placing major infrastructure, which at that time were the canal systems.
The first countrywide geological maps of Scotland weren't published until 1835, based posthumously on the work of John McCulloch.
Let's look at some of this for the northwest Highlands of Scotland. And it's a pretty sketchy map. Not surprising, it was a pretty much solo effort by McCulloch. Many of the inconsistencies in McCulloch's mapping had to wait 20 years before they were really picked up, and attention started again really in the middle part of the 1850s. And an example of some of the understanding could be seen in this map here that was put together by Murchison in the later part of the 1850s. It's also a pretty sketchy map. It doesn't show anything like the detail of Smith's mapping in England. We'll look at some of the reasons for that shortly, but it's worth pointing out, of course, that the quality of geological mapping in Scotland was at a pretty high standard in the middle part of the 19th century. Murchison at the time was Director General of the Geological Survey and was responsible for generating highly accurate and detailed maps for many important areas in the central belt. So let's go to the headquarters area of the Geological Survey and have a look at the map of the time around Edinburgh. So this is the Edinburgh sheet published in 1859. You can see how old it is. It predates the Forth Railway Bridge, for example. Let's go and just look at some of the mapping down here. And here's the detail of Arthur's Seat and central Edinburgh, obviously much smaller than it is today. But look at the detail as we come to this area of the map around Portobello and then inland towards the estates of Dalkeith. All this really fine detail. So what was the motivation for this amount of detail and this type of mapping? Well, a look at the key provides the answer to why there's this detail on the eastern side of this map. The grey units here are coal measures. Indeed, all these little seams that you can see running across the map through this blue area are also coal formations. Well, let's place this map in the context of the society in the middle part of the 19th century, particularly of the working population working underground. Well, not only were working conditions horrendous for miners, indeed their entire families who often worked alongside each other underground, but also the numerous accidents. So from 1842 onwards, legislation was gradually brought in that first of all limited who could work underground, and then the requirement that mines should be managed and supervised by qualified people. So this created a training demand.
Well, this training need is quite considerable. In 1860, there were 435 registered coal pits in the central belt of Scotland. And alongside that, there'll also be a number of subsurface workings of things like iron ore. All of these need qualified mine managers and superintendents. In 1859, the year the map was published, Glasgow School of Mines opens at Andersonian College, which eventually becomes incorporated into what is now Strathclyde University. So there's an opportunity here to provide training materials for this generational shift to mine managers. And this is where the Geological Survey comes in. In addition, of course, those 435 distinct coal pits are owned by dozens of different owners. So there's a real need to share and compile information of the subsurface and how to work coal across all of the central belt. And the Geological Survey are an ideal organisation to do that compilation. This 1859 sheet is just a summary. It's based on what they term these 6-inch sheets. This is mapping at a scale of 6 inches to a mile, which is 1 in 10,560, so enormously detailed, and there's a lot of richness in this map. We can recognise, for example, this layer of blue, which is a limestone. You can see that it's marked with these symbols with arrows, which tell you about the inclination of that limestone layer. You can also see all these individual coal seams labelled and mapped out through the entire area. So how is this information used by geologists to not only establish how these coal seams link together, but also how do we understand where they project in the subsurface? Well, let's look at some of the other materials that were put together. And these are the really remarkable correlations from one location to the other of all the various coal seams shown in black from one location across. And then using the knowledge of the sequence of the coal seams and their related strata, you can build them up into these remarkable cross sections with huge detail. And all the way across, even onto Arthur's Seat. Not that there's any coal up there. So fantastic detail and great skill demonstrated here by the work of the Geological Survey in the 1850s, early 1860s around Edinburgh. And of course all that intricate surveying of the geology is allowed because the topographic survey upon which the geological maps are printed is also really detailed. You can see the fledgling railway lines coming out from Edinburgh. You can see the street plan within the new town. You can see all the lanes and streams in all the countryside around. So having a good topographic map is fundamental to being able to make a good geological map. Of course, things didn't stop here with this version of the map. In fact, the Edinburgh sheet has continued to be
modified and developed and edited and improved in the following years. This is for example, the 1930 version of that classic map sheet with the cross section and the stratigraphic columns on the side, showing how the coal seams can be mapped and traced around the region. In addition, some of the key players involved in this mapping eventually wrote up the methods, and they became standard ways of teaching students how to make geological maps. For example, this classic textbook by James Geological, Structural and Field Geology, goes into the methods with some really clear diagrams as to how you can go about making geological maps from basic field observations. So you can see what he calls a skeleton geological map, which shows the field data, which is in here essentially some stream sections, and the continuity of beds immediately around these stream sections, some coals measured, there's some dikes and so forth, and bedding orientations, the orientations of the stratification shown by those symbols there. And then you take the basic observations and then complete a geological map by extrapolating and interpolating between the stream sections, and then finally showing everything on a cross section to show how the map pattern works in 3 dimensions. And you can even build up a geological story to show that the rock layers were laid down, then folded and faulted and intruded then by these various intrusion bodies. So there's a history that we can build from the geological map. So that's the basics of the geological map approach. But we move rather ahead in our story here. Let's go back now to the middle part of the 19th century and move away from the Edinburgh area and back up to the Northwest Highlands.
And it's not been surveyed in anything like the same detail. So this is an example of the type of base map available to geologists working in the 1850s in the Northwest Highlands. In general, the coastlines are really excellent, as are the main thoroughfares through the landscape. But inland, the mountains and so forth are really sketchy. Many are in the wrong place. Some of the valleys don't link up in the way in which we know them to link today. It's wilderness. Mapping in those sorts of situations is clearly going to be a challenge. And it's also a long way from home. Access is difficult. And the socio-economic drivers of detail mapping that come from the Central Belt are not the same for understanding the geology in the Northern Highlands.
In this context, Murchison's sketch map of 1859 isn't a bad job. Reconnaissance maps are really important for driving science forward, for focusing future work and inspiring others to get involved. Murchison didn't see it like this. He thought his work was entirely correct. Indeed, his approach was to shout down dissenting voices. In his mind, his interpretations, and therefore those of the Geological Survey under his direction, were simply unassailable. Not, of course, that there were many dissenting voices in the middle part of the 19th century, but there was one, and that was James Nicol, Professor of Geology at the University of Aberdeen. And this is his map. It tells a different story. While Murchison thought that the rocks formed an unbroken sequence getting younger from west to east across the Northern Highlands, Nicol interpreted tectonic disruption. The rocks had been faulted together. This disagreement is called the Highlands Controversy, and the nature of the debate hindered scientific investigation for the best part of a quarter of a century. Murchison and his successor, Archibald Geological, continued to close down any kind of scientific discussion. It was a dangerous game. This is Geological's map from 1876. Just compare the detail of the Edinburgh area, which, as we've seen, is based on careful, detailed mapping, with that for the Northwest Highlands. Like Murchison's map, this version is still really sketchy. There's little attention to detail. This work was based on short trips, rapid walks through wild country, and next to no intellectual challenge, such as you might get by looking at rocks in the company of others. But that was soon to change. and we can see the winds of change in the base map if we look through the geological colouring on Geekie's map. The railways have arrived. The Highland Railway arrived here in Legg in 1870 and in Achnasheen 2 further south in Wester Ross. A comfortable train journey followed by a few hours of coach travel could get geologists out to the critical ground in the Northwest Highlands. And came they did. Through the later part of the 1870s and into the early 1880s, a series of geologists came to the Northwest Highlands looking at the geology, and they began to challenge the Murchison-Geekie doctrine. The key player, though, was Charles Lapworth, Professor of Geology in the University of Birmingham, who brought careful geological mapping, and here's part of his map for the Erebol district. And it changed everything. He showed that the rock sequences had indeed, as Nicol thought, been faulted together. But the scale of faulting that Lapworth demonstrated was at an entirely different level. Well, as Lapworth was beginning his work in the Durness and Loch Erebol area, there were two members of the Geological Survey who were also working up there. They became convinced of Lapworth's ideas, and so late in the season of 1884 they strongly encouraged their boss, Archibald Geekie, to come and have a look. Those geologists were named Ben Peach and John Horne, and faced with the evidence that they showed based on Lapworth's ideas, Geekie had to change his mind. The Murchison doctrine collapsed overnight. To Geekie's credit, as the director of the Geological Survey, he directed his crack troops of geological mappers in the following years to go up and map this ground properly, bringing to the ground the careful techniques that the survey had employed routinely in the central belt of Scotland. And this work is summarised in Geekie's 1892 map of Scotland. Just look at the new detail here in the Northwest Highlands. Well, let's take a look at some of the really detailed mapping that was done in the Northwest Highlands in the 1880s by Peach, Horne and colleagues when they got to grips with this ground. And we can go and visit some of their work here in the Assynt district in Sutherland. So this is part of one of the maps that they made on the ground. These are what geologists call field slips. And it's the detail of the topographic base map that, just as we saw around Edinburgh, allows precision in geological surveying. And just like Edinburgh, these are at a scale of 1 to 10,560. That's 6 inches to the mile, so approximately 10 metres on the ground is represented by 1 millimetre on the map. Peach and Horne carefully recorded the geology in stream sections and in areas of good outcrop, and where the scale of the map was insufficient to record the detail, the geologists made more detailed sketches on the back of their field slips. So from the basic field observations, the geologists could then interpolate between the outcrops to create a complete field slip. And then they summarised this in what they called a clean copy, which, if you like, is a final statement of the geology. And then all that detail was knocked back, and the final published map was a simplified version at a scale of 1 inch to the mile. And this is the map. It's this area here we've just been looking at, and it's still got remarkable detail in it. Well, okay, so much for the Assynt district, but my favourite map sheet of all was one that they produced slightly later and further south, and it's this one here for the ground, well, from Ullapool, which is just off the top of the map, down to Kinloch here in Wester Ross. Now, this map splits geologically into two parts, straight down the middle here, from an eastern area with these yellow rocks to this more, well, variable material out here on the west. So, to understand the relationships on maps, I find it useful to sketch little cross sections to show how the geology works in 3 dimensions. So let's have a go at that through this area down in here. Well, we're going to draw a cross section roughly through this ground through here, and that distance on the ground is about 10 kilometres, and these hills are going up to Munro, so let's say they go up to about 1 kilometre above sea level. So there's about 1 kilometre relief in 10 kilometres sideways. So we've got our scale, something like this, where that will be 1 kilometre above sea level, and we can now start putting some topography on this. As we walk across here, we go across Rustat Moor, which is a shade under 1,000 metres, then down into the valley bottom in here, back onto the top of here, and down into this valley in here, where there's this little loch, which is Loch and Nid, and then back onto the top of the hills up here. So we go from high ground to low ground, gradually up to high ground, drop steeply off to this valley, and then up onto the hills here. So if we put Rustat Moor about there, the valley bottom about here, the other hilltop about here, Loch and Nid about there, the other hill something like this. So we have a landscape that does something like that through this countryside. Well, I will just label this up. That would be west, north, west. That would be east, south, east, and that's about 1 kilometre. Something I tell my students, it's quite important when drawing cross sections to try and keep the vertical and horizontal scales equal, so that the orientations of features that we deduce from the map or from outcrop are mirrored in what we plot on our profile. Okay, now let's put some geology on. Well, we can see that the ground around here, the low ground in the valley bottom in here, is this stripy material, which are old gneisses, and they're overlain by this material here, that if I look at the key, is called Torridonian. So we have sedimentary rocks sitting as a patch on top of this ground. So I'm just going to cartoon this in, something like that, so that we have our Torridonian group sitting on the hill, surrounded on the west and in the valley bottom here by this strip of old gneisses. And then the Torridonian comes over onto this side on the valley. So let's colour that in. I'll just colour in some brown for the Torridonian on here, something like that, just to represent that unit in there. We'll keep going in a minute. And that's underlain by these gneisses, which I'll just draw in this, and I'll show that they're discordant, which I'll just point out in a minute by the change in my stroke direction in my colouring there. And here's the discordance that we can see on the map, where these stripes of green are truncated by the edge of the brown. We can see it really clearly here, and also around this area here just north of Rustat Moor. So that feature there is what a geologist calls an unconformity, and I'll label it UNC. Right, let's continue up, and as we go to the top of the hill here, onto this ground on here, we can see that we go into this material here, which lies on the slopes only on the eastern side of this hilltop. So there's a material in here, and I'll just colour this in, well, it's sort of steely grey, but I'll colour it in blue, and that goes all the way down to Loch and Nid here. So all that is some other material that sits above the Torridonian. So the interesting thing is, what's the orientation of the boundary? Does it come down like this or like that? Well, the map pattern suggests very clearly that this layer is just a veneer on this hillside, so that as you go north, it's only seen on the hilltop and on the valley bottom. So this is a boundary that is inclined something like this, down towards the east-southeast, and is underlain by the Torridon group rocks, the Torridonian, like this. And then presumably the Torridonian are underlain continuously by the old gneisses. something like that. So the question now is, what's the relationship between these two units, the Torridon group, and this stuff in here, which is actually Cambrian, which I see in the key? Well, if I look really carefully on here, I can see that the dips within the Torridon group rocks are quite gentle. So I've just shown the orientation of stratal dips, the bedding in other words, coming through like this in the Torridon group. Whereas in here I can see systematically that these bed dips shown by these arrows, not these ones which are glacial striae, but the single arrows which you see clearly in this part of the map, are inclined down, and they show dips of various degrees, but moderate dips coming down like this. So indeed the dipping beds in this material are parallel more or less to the boundary that I've drawn in. Therefore there's a discordance between the gently dipping rocks below and these more moderately inclined rocks above. So this is another unconformity, another discordance. Let's keep going across, and as we cross Loch and Nid, you can see we've got more. Oh, well, this is interesting, because this material here, which sits on top of this Cambrian, is the same as we see out here. So what we see in this position are these old gneisses sitting back on top. And indeed, if you look here on this strange outcrop, you can see that this is a little pimple, which would be a little patch of it just sitting preserved, something like that. But otherwise, we'll have it sitting here. So I'll just draw this on. These are these old gneisses repeated on top. So there must be some kind of fault contact. You see the idea that this little patch here is just an erosional remnant. The fancy word for that is a clipper. Okay, and then as we come up the hillside here, we go into the yellow rocks, and these are essentially parallel, at least the boundary is parallel to the underlying strata, more or less. It tracks the general trend through here. So there's another contact through here, like this, which has got the yellow rocks sitting on top. So there is, and we won't worry too much about what's going on over in this position, except there's clearly some quite complicated interleaving of these sort of pinker and yellowy material in here, which are both in here called the Moyne series, different parts of the Moyne series. So I'll just call this Moyne. These are Cambrian, that's the blue on my cross section, and this is the Torridonian, and these are the old gneisses rocks that we now call the Lewisian, and they occur here as well. So there is our functioning cross section to show the relationships between the main rock units in this central part of the map. So this tectonic structure that carries the Moyne rocks and their little slice of Lewisian over the Cambrian and Torridonian and Lewisian of the area out to the west, well, this is the Moyne thrust. It's a major tectonic structure that you can trace from the north coast of Scotland all the way down to the Isle of Skye. And its structure was established more or less in every detail by Peach and Horn and colleagues in the 1880s. Their work changed the way in which geologists viewed the tectonics of the Earth's crust. A really remarkable piece of work. This area also has historical significance because in 1860, some 24 years before his conversion to the idea of thrust tectonics, Archibald Geikie walked this ground in a day and thought that he saw stratigraphic continuity. In other words, he supported that old Murchison idea. 24 years later, he changed his mind, and then eventually he took those ideas and the ideas we've just demonstrated in this cross section and published them in his textbook on geology. And this is his cross section he used to illustrate the importance of thrust tectonics, these thrusts marked by T, repeating stratigraphic units, stacking up the crust. So this area north of Loch Maree became really important for demonstrating this idea of thrust tectonics. We could use this cross-section to build up a geological history, of course. The youngest thing that's happened is the emplacement of all these Moyne rocks out over here towards the west-northwest. Before all that happened, well, we've had the Lewisian gneiss and its history. It's been uplifted and eroded, and then the Torridonian's been deposited on top, and then actually that's been tilted, then the Cambrian deposited, and then they're being tilted back again. So there's a really complicated history that we can gradually build up. Well, nowadays we know that the Moyne Thrust and its associated structures are about 430 million years old. There's a much older history of deformation recorded by the Lewisian rocks, which were of course there long before the Moyne Thrust was formed. And we can see this early history expressed in the map, but also in outcrop really spectacularly around the coast of Grunard Bay up here in the northwest corner of our map. And the rocks at Grunard show spectacular, complicated igneous and deformation histories. By that we can recognise series of different intrusive events of different types of igneous rock that have built up and intruded each other to create the continental crust. This crust forming event and the related deformation that immediately followed it are somewhere around 3 to 2.8 billion years old. But the story doesn't end there, because that crust continues to deform, and we can see fantastic structures in it as the layers have been folded around and interleaved together. And then all that geology, which happened deep in the crust, has been brought up to the surface, eroded down, and then the Torridonian rocks have been deposited on top. Well, this Lewisian geology that we see on this part of the map actually continues, of course, further to the west, and we can see it continue onto this rather tatty copy of an ancient map here of the Gairloch district, where the Lewisian geologies come through with these green and pink stripes, the same really complicated deformation, and then where everything's sheared out and smeared, and then it being overlain by the Torridon group rocks. So the Gairloch district has some of the oldest geology in the British Isles, preserved in remarkable detail. And the map is superbly detailed too. It was published in 1893, and although the topographic base and geological line work are printed, the geology itself has been painted in by hand using watercolours. And these strips of green, representing narrow bands of amphibolite rock, are really carefully picked out. Well, the Gairloch sheet is one of a whole series of maps published as a result of the mapping by Ben Peach and colleagues in the later part of the 1880s that run down the west side of northern Scotland, and they're a fantastic resource. So let's go on a bit of a tour, starting down here in the Kishorn area. These blue limestones coming through. And then we can nip up to the Ullapool area, and we can see the same sort of geology coming through here. We're going along the Moyne Thrust belt here, and all the way up to Northern Assynt. This fantastic map detail. Well, all this skilled artwork came at a price. If you wanted to buy this map in 1893, in the coloured version, it would have cost you 25 shillings and threepence. That's about £165 in today's money. Different amounts of geological complexity incurred different levels of painting charges. So this map of the Ullapool area and Southern Assynt was 14 shillings, a bargain at £90 in today's money. The painted Gairloch map was 15 shillings and sixpence, essentially £100. Well, clearly, owning a set of these geological maps of the Northern Highlands would not be cheap. But that changed with the application of proper colour printing in the early part of the 20th century. So when the Inverbroom sheet that we've spent some time looking at together was published in 1913, this map retailed for 2 shillings and sixpence, which is about £15 in today's money. What a change. Well, these maps may be things of great beauty and represent stunning pieces of geological research, but at the time, Archibald Geekie, as director of the Geological Survey, received significant criticism for directing so much manpower to the Northwest Highlands, an area where there is no coal and there's very, very little iron ore. So government could see very little socio-economic reasons for doing this kind of quality of work. But this misses the point. I'm sure in Geekie's own mind, he was driven by curiosity, wanting to solve the tectonic riddles of the Northern Highlands. But also, I'm sure he wanted to also demonstrate the quality of work that the Geological Survey was capable of, which would then give more confidence to government and others as to what they were doing elsewhere in Scotland. And the payoff is this superb resource, which has underpinned training for geologists all around the world for well over a century. Of course, these days, geological mapping in the UK is available digitally via the British Geological Survey's open portal. But the use of digital technologies is just the current end point in our story of technology in the use of geological mapping. We've seen that actually it's the quality of base map that's driven precision and geological understanding as we moved out of the later part of the 19th century. And access through the availability of railways has also been really important in driving forward the geological discoveries. And technology continues today, of course. Nowadays, you can map digitally direct onto ruggedized tablets or your phone using GPS to assist in locating. Though I prefer to still use pencil and paper in the field, that's partly because it's easier to edit using a pencil and an eraser, and additionally your pencil won't run out of battery charge. Technology has also changed where we can map. Let's look at Geekie's summary map of Scotland from 1910. What's missing? The offshore. Geology doesn't end at the coastline, it continues under the sea. And for that, obviously, we need to use technology, and particularly geophysical surveys. So, since around 1970, the BGS, its precursor organisations, have variously surveyed the Minches, as well as much of the UK's continental shelf. Not only have these mapped the bedrock on the seabed, so that we can recognise these igneous rocks in the purple, but also it's looked deep into the earth to look at crustal structure beneath northern Scotland. So amongst all these seismic surveys, only a few look really deep, and we'll look at one of them, the so-called Grid 07 line here, running through the northern Minches. This is the seismic profile, and it reveals structure. We can pick out the base of the crust, the so-called moho, and we can also see in the shallow section with the crust the sedimentary basin that underlies the Minches. There's Torridon group rocks overlying the whizzing crust, and in blue, younger strata of Triassic and Jurassic age. So the seismic data reveals how the surface geology that we can map onshore passes to deeper in the crust and goes beneath the basin that underlies the sea of the Minches. The seismic reflection method allows us to map through the whole of the crust, and we need the surface geology, the mapping, to calibrate how we interpret the seismic data. Put them together and we create a 3D understanding of the outer part of the Earth. And unlike our 19th century forerunners, geologists today can use images from space to map active dune systems, for example. Google Earth is a major resource for us for training and research. And of course, it's not just about planet Earth. The logo reveals these dunes are on Mars, where ideas of surface geology mapped from satellite are now being tested on the ground. The Martian rovers like Perseverance provide geologists back on Earth with the senses, the information they need to create geological interpretations. And plenty of geological challenges remain on Earth. We still need to understand the subsurface. Today it might not be so much about finding coal, but these coal seams represent important geothermal resources now, and the surrounding sand beds are important aquifers. So understanding the Earth's subsurface remains as important today as it did during the Industrial Revolution. And geologists still need to be trained in how to create field maps. The Northwest Highlands still provides a really important training environment for future generations of geologists, and all that understanding is underpinned by geological maps originating from the later part of the 19th century. There's a heritage that links the modern geologist back to the discoveries of the 19th century. I've been Rob Butler. I hope you've enjoyed this tour of these wonderful geological maps.